Hello, everyone. Good evening. Welcome to a Leitner Observatory live stream on this Tuesday night, January 4th. I'm looking out over the observing deck at the Leitner Observatory here. It's a quiet, cold, mostly clear night. Skies are starting to get cloudy. However, let me turn on my camera here. There I am. Hello, everyone. I'm here in the control room at the Leitner Observatory inside. It's not terribly cold out. It's about 28 degrees outside, according to our weather station out there. And it's clear now, but not sure if it's going to stay clear. So let me take a look here at the chat. If anyone has any questions as I am doing my observing session, feel free to type it in the chat. I'll be happy to try to answer any questions that I see. We had been doing in-person observing sessions on Tuesday nights. That's normally our main public outreach program here at the observatory, is to open the building and do planetarium shows and lectures and things on Tuesday nights. And since July, I think, of this year, well, of 2021 anyway, happy 2022, everyone. Since July of this year, we've been doing in-person observing outside on the observing deck when it's clear on Tuesday nights. We've had to pause that for a little while because of the COVID case counts in Connecticut, and Yale has gone to a higher alert level, meaning some of the public buildings are shut down and gatherings aren't allowed and so forth. So we'll keep an eye on that and hopefully eventually be able to go back to in-person observing sessions and eventually back into public planetarium shows inside the building. Hi, Fred. Happy New Year. Thanks for tuning in for the live stream. It's a bit later tonight. I had been doing some live streams during COVID on Tuesday nights earlier in the evening and talking about what's up in the sky and pointing the telescope at planets and so forth. We had a really great view of Venus and then Saturn and then Jupiter up in the evening sky, all fall and winter. So we had some really great views at public night of those and got to show some of my students those three planets in a row, which was really fun. It's quiet now. The students are off campus and I'm up here at 10 o'clock tonight. Because I was thinking it would be interesting to try to track the James Webb Space Telescope, which of course was finally launched on Christmas morning, December 25th, 2021, after many decades of work in design and under construction for 25 years and delayed for many years. I feel like sort of last 5 or 6 years, there were many delays in launch of the James Webb Space Telescope, sometimes called the successor to Hubble, but it's really a different telescope with a segmented mirror tuned to the infrared rather than visible and ultraviolet, orbiting the sun at the Lagrange point rather than orbiting the Earth like Hubble was Earth orbiting telescope. But it certainly is a space telescope that's designed to produce images and spectra, some amazing science goals, a whole new window on the universe. And it was very exciting to get to see James Webb launched on Christmas, and then to keep track of the progress as it makes its million-mile trip out to the Sun-Earth Lagrange point. So if you haven't been paying attention to the news about James Webb, it's definitely worth following the NASA YouTube channel and taking a look at the JWST NASA website, catching up with what's going on. And there was a big milestone today in that finally they finished expanding the sun shield, so tensioning the sun shield. There's this several layer sun shield made of plastic with aluminum, so it's shiny, very reflective. And that's actually what protects the body of the telescope from the heat of the sun. And so an important part of keeping it cold and being able to do the infrared observations that it's going to do. I'm not going to talk too much about the science of JWST or the engineering of it. There are much better YouTube channels out there and articles about it if you're interested in following that. Although if anyone wants to ask a question in the chat, I'd be happy to try and answer it. Right now, JWST is about 580,000 miles from Earth. That's about 3 times the distance to the moon. And it's heading out to this so-called L2, the Lagrange 2 point, that's just beyond the orbit of the Earth around the sun. Normally, if an object is orbiting the sun closer to the sun than the Earth, it will orbit faster. And so it'll have a period shorter than a year. And if it's a little bit further away, it'll orbit more slowly. And it'll have a period longer than a year. So you wouldn't expect it to track with the Earth because it's a little bit further away from the sun. About 1,000,000 miles is about 1%, a little more than 1% of the distance from the Earth to the sun. The distance from the Earth to the sun is 93 million miles. L2 is out at 1 million, a little bit further along. But there's a really interesting gravitational stable point just beyond the orbit of the Earth, where the gravity of the Earth pulls an object, satellite, asteroid, whatever it happens to be, a little bit faster, and the object can kind of tag along with the Earth in its orbit. We've had spacecraft out at L2 before. If I remember correctly, the Planck spacecraft, which is a microwave telescope designed to study the cosmic microwave background radiation, it was out there for a while. It's not quite a stable point in an orbit. If an object at L2 moves a little bit above or below the plane of the orbit of the Earth, it'll get pulled back. So that's stable. It's kind of like a marble in a bowl. If the marble goes away from the center of the bowl, it'll swing back to the middle. And also, if the satellite moves closer or further away from the Earth, it'll go back to the equilibrium point. But if it gets a little bit off, ahead, or behind its orbit, that's an unstable equilibrium. So that's like the marble on top of the hill, or it's like trying to balance an umbrella. I don't have an umbrella handy. It's like trying to balance an umbrella in your hand. And if you get it perfectly balanced, that's great. But if it tips a little bit over, it will start to accelerate and fall over. So you can try and move your hand and keep it balanced and keep it at that equilibrium point. And so when the James Webb telescope gets to the L2 point, it's actually going to make a little circular orbit around the point to kind of keep it near that stable point. And it can stay there as long as it has propellant. The rockets, the maneuvering thrusters, have propellant to keep it there. And then after that, it's going to drift away slowly, and we'll lose track of it. Now, I was thinking that the size of JWST, it's about 20 by 14 meters. So 20 meters in the long direction, 14 meters this direction. And it's only, like I said, about 3 or 4 times the distance of the moon. And we often will track asteroids using our telescope here, using the 16-inch telescope here, which you can see in the live view of the deck. So this dome way over here on the far right houses our 16-inch or our 0.4 meter reflecting telescope, which is the telescope we use for our advanced student labs and research projects and things like that. And in the summers, sometimes we use the telescope to study the trajectories of asteroids, minor planets, especially near-Earth asteroids. And there are quite a few that are smaller than James Webb, that are further away than James Webb, which we can track with our telescope. They're certainly bright enough, even though they're not very reflective. If I actually look at spaceweather.com and scroll down here to the bottom, we can see some near-Earth asteroid encounters. Let's see, today is January 4th. So, for example, tomorrow we're going to have a flyby of this asteroid 2021 YQ. It's going to be at 6 times the distance of the moon. At this speed, 15 kilometers per second, that's pretty fast. It's 64 meters across. So that's bigger than James Webb, but it wouldn't be hard for us to see that with our telescope. We could probably track that asteroid. So I was thinking it should be possible to see the telescope with the James Webb telescope with our telescope as it flies out, especially now that the sun shield is fully deployed. So it's going to be big and reflective. And it's still relatively close. It's, 65% of the distance out there. It's heading out towards the ecliptic plane. It's going to be interesting, the path that it takes relative to the stars once it gets to L2. We look at the sun and we see the sun moving through the zodiac once per year as the Earth orbits the sun. Kind of the line of sight from the Earth to the sun sweeps around the sky. It takes 365 days for the sun to appear to go all the way around 360 degrees around the ecliptic. So the sun's moving about a degree per day relative to the background stars. We have these 12 signs of the zodiac, so that the sun is in a different zodiac sign about every 30 days or about every month or so. James Webb at L2 is always going to be opposite the sun as we both orbit around the sun. So when the sun sets, the telescope rises, and it should be near the ecliptic opposite the sun no matter the time of year. So it's going to be creeping along 1 degree per day along the ecliptic. Well, let's see if we can find it before it gets cloudy tonight. Let's connect to the telescope and see if we can see it. Now, how can we possibly know where to look? This map here is not going to be helpful. If I want to know where anything in the solar system is, what I'll do is look at the JPL Horizons database. So JPL is, of course, tracking the planets and asteroids, comets, spacecraft, everything. JPL has a very good ephemeris. Ephemeris is basically a list, a table of the positions of an object in the solar system as a function of time. So at 10 o'clock, it's here. At 10:30, it's here. 11 o'clock, it's here, and so forth. And of course, they're basing this on very advanced computer simulations. So I can go to the Horizons website right here. You can do it as well if you like. And there are a couple of different ways to access the database. I'm using the Webb app right here. And my target is the James Webb Space Telescope, JWST. I could change that to an asteroid or Mars or anything. My observing location is the Leitner Observatory. We have our own observatory code, so it knows where we are. And then the time, I'm observing on January 5th, Universal Time. So Universal Time is basically like Greenwich Mean Time. It's 5 hours ahead of Eastern Standard Time. There's some pedantic differences between Greenwich Time and Universal Time. But right now, the time is 3:12 and 26 seconds UT. My local star time is this. That tells me what celestial coordinates are overhead from my observatory right now. So it's already tomorrow. It's already January 5th Universal Time. So that's the time that I want, is the day from 0 hour midnight Universal Time, January 5th to January 10th, every 10 minutes. And I clicked on Generate Ephemeris already, so I've got my results here. So this is the data that I get from JPL. Lots of information about the object, the telescope. It's some information about the observatory, or where I'm observing from. But here's what I really want. These are the positions of the telescope, the James Webb Space Telescope, as seen from New Haven tonight. Now, what's the UT right now? It's 3:13. So if I scroll down here to 3:10, 3:20, this is the closest time that I requested. So at this moment, or at 3:10, it was at this celestial longitude and this celestial latitude. And then these coordinates are useful as well. This is its azimuth. That's where it is around the horizon. If you wanted to point a telescope at it using cardinal directions, north, south, east, west, you would point at a heading of 154 degrees, kind of southeast. And then here's the angle to the horizon. So when you point in that direction, you crank your telescope up to 47 degrees or 46.679949 degrees. And you should be pointed right at the position of the space telescope. Now, of course, that changes as the Earth turns. So, and it changes as the telescope flies through space. But I should be able to put these coordinates into my telescope pointing software and take some pictures and hopefully see the spacecraft as it flies out there. So I'm going to now connect to the observatory computer, and I have already pointed the telescope, my 16-inch telescope, out in the observatory dome, approximately where James Webb should be out there in space. It's kind of a little bit to the left of the constellation of Orion. It's kind of in the plane of the Milky Way, so there are going to be a lot of background stars. That's actually not so great, because then you have to figure out, okay, which point of light is the telescope and which point of light is which are stars. The stars really don't move very much relative to each other over the course of a few minutes, but as the telescope is flying out to L2, it still actually needs to fly quite a bit to get to the ecliptic. It's going to be in the plane of the ecliptic. Now, it launched from the Earth's equator. So it starts off in the Earth's equatorial plane, but it's heading north, and it's going to head up to the ecliptic. Now, I have a camera on the telescope, so I can switch over here and take a quick picture. So we'll just take a 15-second exposure with the camera. If you'd like to see what what's in the dome, this is a security camera that's attached to the side of the telescope, and this helps me see if the telescope is actually pointing out the opening that's in the observatory dome. So, or if I'm looking at the dome, looks like it wouldn't be a bad idea actually to rotate the dome a few degrees to get a better view. Well, here's the picture that I just got. So, I see a lot of points of light. Let me before I talk about this picture, let me rotate the dome a little bit. So I'm going to open my dome controls here, and I think if I rotate this way a little bit, there we go. I had a good view out the dome, out the shutter opening, but it doesn't hurt to give it a little bit more room. I can see two bright stars through the slit, through the security camera. That's probably Sirius and Betelgeuse. Those are the two bright stars that are kind of on that line in the direction that we're pointing. And now if I go back to this image, lots and lots of stars there, but we're looking for something that's moving. And I saw it earlier tonight, so I'm pretty sure I can figure out which one it is. Yeah, just the brightness and contrast a little bit. This is a basically live image. I mean, I took it a few seconds ago. And what I'm going to do, what I might actually do is put in the most up-to-date coordinates to make sure we're pointing in the right place. But let's take a sequence of images, kind of like a really slow video image. We're going to take 20 15-second exposures here. So 15 seconds, repeat 20 times. And I'm going to save these to the hard drive of the computer so that if I want to go back and analyze the images later, I can do that. The other thing I might do is just zoom in on my finder chart here and just see if the pattern of stars I see in my image matches what I see in the star chart. So if I just zoom in on where the telescope is right now and drag this over so I can see, this purple box on my star chart is a representation of the field of view of the telescope. So yeah, this bright star right here is definitely this bright star right here, and this bright star right here is definitely this bright star here. So I'm doing some star pattern matching so that I know I'm sort of in the right place. All right, so let's start taking images, and we're looking for something, a point of light in this image that's moving. So we'll start making our little movie, 20-frame movie. Normally a movie, they tell you the speed of the movie in frames per second, but this is going to be in seconds per frame. Oh, there's another satellite. There's another satellite flying through my image. UFO. I thought I saw something move, but I'm not 100% sure. Oh, there it goes. I think it's going to be over in this part of the image, the motion that I'm expecting. Is it that one right there? Here comes the next image. Someone say something if you see a star move. I didn't see that move very much, so maybe that's not the right one. Is it that one? Once I have these 20 images saved, I can also blink through them, and then we'll definitely see if there's anything moving in the frame. We'll definitely see it. every so often my software glitches and you see a flash of yellow, so that's not important. All right, here comes the next image. Oh, I don't think I saw it move there. Anyone see anything moving? I think it's based on how bright it appeared. I still think it could be that. Here comes the next image. Oh. When we get to, say, 10 images that we've taken, I'll load them up in the blinker, and then we can track it down. Kathy, you saw it? You think you see where it is? Okay, here it comes. Next image. I did see it. I don't see it moving. All right, I'm going to cheat, and I'm going to load the last set of images. Let's see. This was image 3766. So I'm going to go over here to my blinker, and I'm going to close all of these images that I opened earlier. All right. And I'm going to open the most recent sets of images, which include, let's see. So I got 3767, and I can go back to sort of here and open all those images. Yeah, there's that image with the satellite. So first thing I'm going to do is align the images. You know, this is kind of wonky. You see it moving northwest, passing between the top two brighter stars. Yeah, northwest is the direction that it should be moving based on the coordinates that I saw. I'm going to align these images with each other so that then we can blink. Okay, that'll take a second for the computer to calculate. And I'm going to say view, blink. Okay. And now we should be able to blink through the images. Oh yeah, that's it right there. I was thinking it was that, but there it goes, moving across the sky. And there's a much, much closer low Earth orbiting satellite. I don't know what satellite that is. We could go look it up. But there's James Webb Space Telescope heading out. I actually looked at it last night, and tonight it looks a little bit brighter, and it looks like it's moving a little slower, sort of from our point of view. All right, let's go find it in the live images. So those two bright stars, and it's right in there. So if we switch back to here, it's one of these stars in here. I think it might be that one. Let's see if that one moves. Oh, yep, that's it. All right. Well, we were successful in finding James Webb Space Telescope. We have photons from the sun heading out, missing the Earth, going a little bit further, 3 light seconds further, and hitting the sun shield of James Webb Space Telescope and bouncing off of the sun shield, coming back, traveling through the Earth's atmosphere, coming down to New Haven, passing through the opening in our dome, being focused by the aluminum mirror on our telescope, and then being detected by our little CCD camera as it flies on its way out to the L2 point. Now, this object, the space telescope is going to be, like I said, hanging out opposite the sun in the ecliptic. Any night of the year, if you have a telescope that's big enough, let's see, how bright is it in terms of magnitude? I expect that that's about a 15th magnitude object compared to some of the other stars that I see nearby. Now, I think what I'll do tomorrow when I have some time is I will look at these images and actually do some measurements actually see how bright is it really. But I think a telescope of maybe a 10-inch aperture, 12-inch aperture, with a consumer camera, DSLR, something like that, should be able to take pictures of James Webb Space Telescope as it's out there, as it is taking pictures of the most distant stars in the universe, the first stars in the first galaxies, as is one of its important astrophysics missions, and as it studies the atmospheres of distant exoplanets. I'm going to actually, my images stop, and I'm going to continue taking images so I can keep watching it move. As the telescope is studying the distant atmospheres of exoplanets and looking for signs of life in the form of oxygen or methane or other exciting things, we can actually take a look at it as well. Let's see. Kathy's asking, what are those 3 bright stars? So these 3 stars right here, just one of the random stars in the Milky Way. We could look at the star chart and see what their catalog numbers are. So those 3 bright stars are the same as these 3 stars on the chart. So for example, that star right there, if I click on it, is a star called Tycho 133:1284. Does it have another name? Let's see. This is a better name, SAO 113842. Why is that a better name? This is the Smithsonian Astrophysical Observatory catalog. It's an older catalog, so I'm more familiar with the stars in that catalog. It's a star with a magnitude of 9.02. So yeah, it's a pretty bright star. You would be able to see it, that star right there, you would be able to see it in a medium-sized telescope. So Fred's asking, so even when JWST arrives at the L2 point, it'll still be visible? Yes. Now, it'll be fainter because it's going to be further away. It's going to be, we're still getting images, yes. Which one is it again? It's that one, right? Yeah, it's still that one. So I've got my cursor pointing at it. We could zoom in even a little bit more on it. So that one, I think. Let's see if I'm right. Yeah, that's it. Now I'm zoomed in enough you can see the individual pixels on the camera. So it appears to be taking up 3 pixels on the camera. Of course, this telescope that's only 20 meters long out at a distance of 600 million miles, we won't see any detail on it, right? On the moon, when you look at the moon with a small telescope, you can see details as small as a few kilometers, 2 kilometers, 3 kilometers. That's 3,000 meters across. So now James Webb is 3 times further away, and it's like a factor of 2 orders of magnitude smaller than the craters on the moon you'd be able to see. So all we're seeing here is just a blip of light, a glint of light. We don't see any details on it. Yeah, but to answer your question, Fred, would your 120 millimeter refractor be able to see it? Well, I don't think you'd be able to see it by eye, because like I said, with your eye to the eyepiece of a telescope, because like I said, this is probably about 15th magnitude. I just ballpark looking at the nearby stars and my estimate of the brightness of those stars. And you would need, that's that's about the same brightness as Pluto, right? And you really, if you're looking visually with your eyeball, you kind of need a 12 to 14 inch telescope to see Pluto with your eye to the eyepiece. A 20-inch will definitely allow you to see it. So if we were to go put an eyepiece on the 16-inch here, and we had dark skies, which we don't. If you had dark skies and a 20-inch telescope, I think you'd be able to see it with your eye. If you're using a 120 millimeter or maybe more like a 300 millimeter telescope with a camera so that you can take a long exposure like this, then I think you'd have a better chance of seeing something. All right. Well, that was a lot of fun. I'm glad that worked out. I'm actually probably going to try to take pictures of JWST on clear nights. There, it's still right there. I'm probably going to try to take pictures of it on clear nights over the next couple of weeks because I'd be interested in seeing if I can plot the trajectory, see if I can solve for the orbit of the spacecraft based on these images of where it is relative to the stars that I'm seeing. And that's kind of a fun project to do with students. And it's kind of also, it's also kind of fun because we're looking at the most advanced telescope ever built by humans out there in space as we're doing it. All right. Well, are there any other questions for the people watching live? What I'll actually do also either tonight when I sign off or tomorrow morning when I get to work is take some of these images and make a time-lapse movie, and I'll post that in the description for this video once it's posted on the Leitner Observatory website. Yeah, Fred. So about a camera, you don't need a very fancy camera. I'm actually working on a video series for the channel about what you can do with a just a digital SLR camera. You know, one that you can buy used for $200 or new for $500. And there's a lot of interesting astrophysics projects that you can do with a camera like that, even with a modest telescope like a 4 or 5 6-inch telescope. So. Okay, well, keep an eye on our website, which is leitnerobservatory.yale.edu, and we'll have announcements there about upcoming public events and upcoming live streams when there's something interesting in the sky. Hopefully we'll be able to open to in-person observing again soon. Who knows, maybe in a month or two when things calm down and the students get back to campus. If anyone has any questions for me, you're welcome to email me. Michael.Faison, Faison @yale.edu. Happy to answer your questions. And otherwise, I'll see you next time. All right. Good night, everyone.